Hello, good morning. Myself, Dr. Shaila Dinkar Apte. Now we'll continue with chapter 4 of Signals and Systems, which is related to the time domain response. So, firstly, we will consider domain response of continuous time system. And here we will be assuming that the system is linear and it is time invariant. And later on we will see how we can modify the system so that we can make use of the LTI filters or the things like that. So how we can make it linear and then use the properties of linear time invariant systems. So we will be learning following things in this lecture. Response of continuous time LTI systems. So what are the types of response? We have zero input response and we have the response to the zero state, that is the relaxed state. So in case when the system is relaxed, we find the response of the system, that is called as zero state response, and we also have zero input response when the input is zero. So we try to represent the system as the impulse response, and we try to represent the input signal xn as the combination of impulses, and then do the convolution integral to find the continuous time LTI system's response. Let us see how we go about doing it. So consider any continuous time system. The response of the system can be found out by solving this particular differential equation. So a generalized differential equation which gives LTI system is given by dn dt n of y plus a n minus 1 dn minus y upon dt n minus y plus a0 y is equal to bm dm dm d dt m of x plus dm minus 1 dm minus 1 dt m minus 1 of x plus etc. a b0 x. So in this case it is a differential equation with the power of n in the denominator and m in the numerator. Now what we'll do is we'll represent this d dt as a differential as capital D. So when we represent capital D, it is assumed that it is the differential. So this equation will transform to d raised to n plus an minus 1 into d raised to n minus 1 etc. up to a0 into it is equal to bm d raised to m plus bm minus 1 d raised to m minus 1 etc. plus b0 into xt. Now when I write yt divided by xt, I will have this term in the numerator and this particular term in the denominator. Now this particular term, that is d raised to n plus an minus 1 dn minus 1 etc. plus a0, this particular term is called as the denominator polynomial. It is also termed as the characteristic equation of the system, because the roots of this characteristic equation will determine the behavior of the system. Now there are a number of cases those will occur. If the degree of the numerator is greater than the degree of the denominator, that is m is greater than n, then in this case high frequency noise will be amplified. So in this case the system is likely to become unstable. But if m is less than n, that is the degree of numerator is less than that of the denominator, we will understand that the system will be stable, no noise will be amplified. Now let us see how to find out the zero input response for the continuous time system. Zero input response, as the name suggests. In this case the input applied to the system is 0 and we are supposed to solve the equation to get the solution of the characteristic polynomial. So we'll have to find the roots of the characteristic polynomial and then we can decide what will be the solution. Okay, to get the characteristic equation, what we are doing is we are replacing d by lambda, capital D by lambda. So the solution can be assumed to be yt is equal to some constant c into e raised to minus lambda t. Right. So if we put d as equal to lambda, then we can write c lambda n e raised to minus lambda n t plus a1 c lambda n raised to 1 e raised to minus lambda t plus a n is equal to 0. This c is a common factor. We can take it out as like this also. Okay. So in this case the input is 0, so the right hand side is 0, and what I get is c as a common factor out, lambda raised to n plus a1 lambda raised to n minus 1 etc. plus a n into e raised to minus lambda n is equal to 0. Okay, this lambda is replacing the differential d, and this lambda e raised to minus lambda t is the solution that we are assuming. Okay. Now, why we are considering this exponential solution? Okay, the roots of the characteristic polynomial are supposed to be the characteristic equation roots, right? Now, these roots or the solutions are written as exponential functions. Why we are writing it as exponential functions? There are two reasons. One is the characteristic equation indicates that all n derivatives of the function are 0. Why? Because lambda raised to n plus lambda raised to n minus 1 etc. plus a n is equal to 0, and when we take the first derivative it will be 0, second derivative it will be 0, third derivative will be 0, all first n minus 1 derivatives will be 0, and this will be true only in case of the exponential functions. For linear time invariant systems, if the input to the system is exponential function, the output will also be the exponential function. So for these two reasons, we are assuming exponential functions as the eigenfunctions of the LTI system. Consider a difference equation given by d square plus 3d plus 2 yt is equal to 0. Now here we are assuming this right hand side as 0 because we are applying 0 input. We are supposed to find the 0 input response given the initial conditions. Initial conditions are y0 is equal to 0 and dy0, that means the first derivative of y evaluated at t equal to 0 is equal to 5. Now what I will do? I will just take this characteristic polynomial d square plus 3d plus 2 equal to 0 and decompose it into number of factors to find out the roots. Now in this case the roots are d is equal to minus 2 and d is equal to minus 1. Now if I know these roots, I can write down the solution yt in the generalized form as some constant c1 e raised to minus 2t, this is for this first root, plus c2 e raised to minus t, this is for the second root, right? Now what is y0? That is the initial condition, it is given as 0. So if I put t equal to 0 in this equation, I get y0 as c1 plus c2 because e raised to term will be equal to 1 in that case. So c1 plus c2 is equal to 0. Then I evaluate the differentiation dyt is equal to, now when I differentiate this I will get minus 2c1 e raised to minus 2t minus c2 e raised to minus t, but it is equal to 5 because it is given as the initial condition. So if I put t equal to 0 in this equation, I will get minus 2c1 is equal to c2 plus 5. But c1 is equal to minus c2 from the first equation. So if I put this, I will get twice c2 is equal to c2 plus 5, and if I evaluate, I will get c2 equal to 5 and c1 equal to minus 5. So if I put this, I will get the solution yt as 5 e raised to minus t minus 5 e raised to minus 2t into ut, because the corresponding system is, or the signal is existing after t greater than or equal to n greater than or equal to 0. Now there is another kind of response that we normally evaluate. It is called a zero state response. Zero state response means the corresponding initial conditions are assumed to be 0, or we say that the system is relaxed. Initial conditions are made 0 and the external input is applied, then we will call it as the zero state response. We will first discuss how to find out the impulse response of the system. So we are assuming that the initial conditions are 0 and the external input is applied. Now what will be the output, or how to find the output of the system? For that, what we evaluate first is the impulse response. So once we know the impulse response of the system, what is the impulse response? It is the response of the system to the unit impulse. So what we are going to do is any input that is applied, we decompose it into scaled and translated combinations of unit impulse. And once we know the impulse response, we can calculate the response to any input, that is to any scaled and translated combination of unit impulse, and that will give you the output of the system, that is called as the zero state response. Now let us see how to find the impulse response. Now the response of the system to the impulse function or the delta function is termed as the impulse response of the system. Now, if a function is functioning, if any system is functioning as a filter, then we find the impulse response of the system and it is called as the filter kernel. Impulse response is then termed as filter kernel or the convolutional kernel. Why convolutional kernel? Because this corresponding kernel will get convolved with the input to find the output. That is why it is called as the convolution kernel, or it is simply termed as kernel. In image processing, impulse response is called as point spread function. So there are different names given to the same function, that is the impulse response. So to find out the impulse response, we will have to apply impulse as input to the system and then find out what will be the output of the system. Any signal can be decomposed into a linear combination of scaled and shifted impulses. So LTI system can be completely characterized by its impulse response. The output is obtained by the convolution of the input signal with the impulse response. Let us see how this is possible. Now, how to find the response of the system? What we'll do is, we'll decompose the input signal into number of impulse scaled and translated impulse functions, then find the response of the system to each of these impulses, and then integrate the response over the entire interval to get the final response. Now, here we go. Now, suppose this input signal is xt is given like this. What we do is, we approximate this to a staircase response like this, and each particular step of the stair will be represented by a delta function, right? So we are decomposing this input signal xt into scaled, because the corresponding amplitude of this particular delta function will change. So scaled and translated, because it is shifted along time axis. So scaled and translated unit impulse. So when we combine all these impulses, we will get the corresponding input signal xt. This is the first step that we'll have to do. Now there is one graphical method for finding the system response. What we do is, decompose the signal xt in terms of scaled and shifted unit impulses as I just indicated. Then find the response of the system to the unit impulse at t equal to 0. That is the impulse response. Now when the system is being shift invariant, when we assume that it is LTI system, it is shift invariant or time invariant, then the response of the system to the impulse at t equal to t1 will be equal to h of t minus t1. So we get the impulse response at any particular time instant t. Now find the overall system response to all the shifted impulses and then add all the responses or integrate it over the entire interval. So we can list out the procedure finding the impulse response of the system. How to find the impulse response? This is the first step in calculating the response. So what we do is find the characteristic equation, that is the denominator polynomial equated to 0. Then find the roots of the characteristic equation. Then impulse response is equal to the scaled impulse added to the characteristic mode terms. That means the solution that we obtain from the characteristic equation is characteristic mode term, and A0 delta t is the scaled impulse which is applied. So in the if the degree of the numerator is same as degree of the denominator, then this A0 delta t it's uh, it will be existing and this A0 will have some finite value. But if m is less than n, we get A0 as 0. And if m is greater than n, obviously we are assuming that the system is unstable, so we are not calculating the response. So there are two cases we consider when m is equal to n and when m is less than n. Now consider one example. Find the impulse response of the system given by. Now this is the equation for the system given d square plus 3d plus 2yt is equal to dxt. Now what is the characteristic equation? D square plus 3d plus 2 equal to 0. So we get the roots of the characteristic equation, d is equal to minus 2, d equal to minus 1. So we can write the solution yt as equal to some constant c1 into e raised to minus 2t for this d1 plus c2 e raised to minus t for this d equal to minus 1. Now we are given the initial conditions y0 equal to 0 and y0 means here there is a bar over this y0. This is supposed to be the differentiation and it is equal to 1. So y0 is equal to d into y0, y0 dash is equal to d into y0, which is the first derivative of y as I told you. Now what is y0? Y0 is c1 plus c2 because e raised to minus 2t will be equal to 1, e raised to minus t will be equal to 1 when t equal to 0. So y0 will be c1 plus c2 is equal to 0 because this is given in the initial condition. Then y0 is y0 dash, that is first differentiation, is minus 2c1, we calculate the first differentiation, minus c2 is equal to 1. But c1 is equal to minus c2. So we get c1 equal to minus c2, which is equal to 1 by solving these two equations. So we can write full solution as yt is equal to e raised to minus 2t plus e raised to minus t by putting the values of c1 and c2 appended by ut. Now in this case, the degree of numerator, which is 1, is less than the degree of denominator, which is 2. So in this case, A0 is equal to 0 and the solution will contain only the characteristic mode terms. Characteristic mode terms are e raised to minus 2t and plus e raised to minus t. These are because of the characteristic equation. So these are called as characteristic mode terms. Now consider one more example. Find the impulse response for the system given by. Now in this case we are having m is equal to n. The solution will contain only the scale response also and the characteristic mode term. So it will contain both the terms now. So the equation is given by d plus 2yt is equal to d plus 1 xt. So as you can clearly see, degree of numerator is same as degree of denominator. That means m is equal to n, and in this case the corresponding a0 delta term will be there. So what is the characteristic equation? Characteristic equation is d plus 2 equal to 0. So find the roots. The root is at d equal to minus 2. So how the solution will be written? Solution will be written as yt is equal to a0 delta t. This is coming because m is equal to n plus c1 into e raised to minus 2t. This is because of the characteristic term. Now what is y dash t? That is the d dt of yt. It is minus 2 c1 into e raised to minus 2t at t equal to 0. This is equal to t is equal to 0. The differentiation of this will be 0. So this is the differentiation will contain only just the characteristic mode term. So minus 2c1 e raised to minus 2t. And what is y0? Y0, when you put delta t is equal to, at t equal to 0, delta t is equal to 1. So y0 is equal to a0 plus c1. This is equal to 0. That is the initial condition. And the differentiation term, that is y bar t is equal to minus 2c1, which is equal to 1. This is given as the initial condition. So c1 will be equal to minus half and also a0 will be equal to half. So we can write yt is equal to minus half e raised to minus 2t ut plus half of delta t, because a0 is also equal to half. So this is how we can calculate the corresponding response of the system which is generated because of the characteristic mode term, and also when m is equal to n we get the corresponding delta function also in the solution. Now what we do? Once we know the impulse response, we are supposed to convolve the impulse response with the corresponding input signal to get the output of the system. So the output can be seen as the weighted sum of the shifted impulse responses. The weights are the amplitudes of the impulse at each given time. So we have considered that diagram. There is a signal and then we decompose it into a staircase input, and each particular component of the stair is the impulse, right? So how to calculate yt? Yt is calculated as xt convolved with ht, which is same as ht convolved with xt. So we'll have to carry out the convolution of impulse response with the input signal xt to get the output signal yt. So procedure for convolution integral. To find a convolution integral, what we do? We'll have to first calculate xt and h of minus t. That means you will have to take the mirror image of xt. You will have to reflect it about tau is equal to 0. Start with time shift t large and negative. So we start with large value of negative, large negative value of t, and go on shifting this x of t minus t towards right until it crosses the signal xt. So increase the time shift t until the functional form of the product changes. Find xt into h of t minus tau and yt, correspondingly find out yt for every new interval, because for every new interval the corresponding value of impulse response may change. Continue this by increasing t in the positive direction, and for each new interval t find y of t. Right. This is the procedure how to convolve the input signal xt with h of t. Right. So we'll continue with how to find the convolution integral and find the response of the system given the impulse response. We will continue with this in the next lecture. Thank you so much.